All right, welcome everybody to the TESS Splinter session. Future Science with TESS. I'm going to talk very slowly as people take their seats. And I will start by introducing myself. I am Nicole Colon. I work at NASA Goddard. You might know me from years on TESS, but I'm here in a new role. Patty Boyd was the former TESS project scientist, and now I have taken over her role as of a few months ago. So, thank you. So I'm very excited to be here to introduce the session. I'm just going to say a couple quick remarks and then hand it off to Avishay, who is chairing the session. So first, welcome. It is great to see so many familiar faces and also new faces here. Well, I guess at least half of your faces with masks. So thank you firstly to Avishay and Rebekah Hounsell for organizing this session. Thank you also to our sponsor, Northrop Grumman, who has provided the food and drinks available to you here. And thank you to the TESS team, who is led by PI George Ricker, walking down the aisle here. So we would not be here today to kick off this session about synergies between TESS and other missions without the hard work of this TESS team that includes many partners and many people that I won't even try to name them all here. It would take too long. But I just wanted to say that if you hadn't heard by now, TESS has been officially extended into its second extended mission that will start in September 2022. So we're very excited, and it would not have been possible without the hard work of the TESS team and also the community who has made amazing use of TESS over the years. So with that, I will hand it off to Avi, who is chairing this session. Thank you.
Thank you, Nicole. We had a few technical difficulties. We hope everything is okay now. For those online, if you can respond in the chat, if you can hear me okay, I will appreciate that. Okay. So we have 5 speakers today. Each of the talks will be 15 minutes for the talk, then 5 minutes for questions. Questions can be asked verbally here in the room or online on the Slack channels for this session, or through the chat through WebEx. As you can see, for this session, we decided to do something a bit different. We are focusing on the future. What can we expect that the science that we will do with TESS data will look like in the next few years and beyond? And I'll invite the first speaker, Susan Mullaly. Susan is working with JWST, and she also has a very, very strong background at transiting planets. So it's only natural that she will give the talk about the planets that JWST will observe. Okay. Okay, now good to go. Susan.
Hello, everybody. Thank you for coming to this session. I am Susan Mullaly. I am the Deputy Project Scientist for the James Webb Space Telescope at the Space Telescope Science Institute, which is the Operations and Science Center for Webb. Yeah, I'm going to tell you about sort of the synergy between JWST and TESS and talk about those exoplanets that TESS discovered that have made it into the first year of observations with the Webb Space Telescope. So just because it's a TESS session, I'll start with Webb. We launched it in December last year on Christmas morning. I hope some of you got up early and saw it. It was an amazing launch. It's a 6.5 meter diameter mirror that is observing in the near and mid infrared, 0.6 to 28 microns. It has more than 90% of its time is open observing time, which means people propose and compete for time on this telescope. And there's a lot it can offer in that it has 4 instruments, near spec, nearest, NearCam, and MIRI being the mid-infrared instrument. And many of these instruments have modes. There's 17 modes, but several of the modes are very good for exoplanets, including imaging and coronagraphic modes, as well as imaging and spectroscopic time series modes, which are especially interesting to this group who's interested in observing transiting exoplanets. I'm not here to talk about JWST in particular and its commissioning. If you want to know more about that, I recommend you come to the JWST Town Hall tomorrow at 6:30. It's in Hall C. So I'll see you there to find out more about that. But let's talk about the science for JWST. Exoplanets is making up about 23%. If you include exoplanets and disks, it's about 23% of the first year of observations with the Webb Space Telescope. And I'm going to walk through a lot of the science that is being covered by these exoplanets. And all of the accepted programs are all available for you at jwst.stsci.edu under science execution. So if you want to know, the abstracts are published. You can go and learn more about the targets and what observing modes they're using. But in general, 6,000 of those 10,000 hours come from people proposing last year to be in the Cycle 1 program. And so that's primarily what I'm going to talk about here, programs that people proposed under exoplanets. So if you look at these science programs, it's split up into kind of 3 broad themes. There's the protoplanetary disks, where people are using spectroscopy to understand the chemistry of these planet-forming disks. There's plenty of people who are studying giant planets, and this is going across both the coronagraphic end, where people are looking for young giant planets, possibly planets as small as Saturn at wide distances from the exoplanets. But there's also people studying giant planets from transiting exoplanets, where they're going to try to characterize their atmospheres in transmission. But where TESS especially has succeeded and has made Webb have real diverse science cases is in the smaller exoplanets. For those planets they discovered smaller than Neptune, where because we have them, we can study the atmospheres of these exoplanets, either in transmission or through a Cliff space curve, so in emission. And as a result, we'll have a diverse understanding of atmospheres for small exoplanets. So to give you a sense of the impact TESS had on the on Cycle 1 exoplanets, this is a plot of just JWST Cycle 1 transiting exoplanets. I'm plotting planet radius versus incident flux, which I know got covered up by the closed captioning, at least here in the room. The color of the dots is based on stellar effective temperature. And so both are relative to the Earth. So I put Earth and Jupiter on there for perspective. So you can see that JWST is observing a wide range of exoplanets, all the way from hot Jupiters, all the way out down to terrestrial-sized Earth-type planets. But you can see those terrestrial Earth-type planets are all orbiting M-dwarf stars. So let me highlight those planets that TESS discovered. As you can see, TESS had a considerable impact on the planets that we are observing smaller than Neptune, so smaller than 3 or 4 Earth radii, making up about half of that program. Additionally, there are a few giant and Neptune-sized planets that TESS has contributed to, actually increasing diversity in other directions for understanding things like planetary evolution and formation. So at this point, I'm going to walk through some of these science programs. This science is not mine. There are loads of PIs who have proposed for this time. And so if you have questions, unfortunately, the programs are all listed at the bottom, so some of you are going to have trouble. So I'll try to make sure I read the PIs of these programs out to you, so you know who's working on this in the next year. But I'll highlight the science case that they propose for and give you a sense of what kind of science is coming out, which is due to these TESS discoveries. Oh, and just so you know, I found that I need to know this information as I think about these planets. So I just created this little code to tell you what kind of planet it's orbiting, what's its size, and what's the log of its incident flux, both relative to Earth. And so this will be sitting next to the names of the planets, because I find the names of the planets tell me almost nothing at this point. There's too many planets. I can't keep them straight in my head. If this is not useful to you, just ignore it. It's useful to me. And so like, the G-type planet giants, you can see up there at the top, and then down here, you'll see M-dwarf planets that are about the same size as the Earth and maybe 10 times the incident flux. So these are the kind of planets we're talking about here. All right, so amongst the giant planets, we'll start at the top, the big planets. One of the TESS discoveries was HIP 67522b, and so this hot Jupiter-sized planet is actually the youngest transiting exoplanet to be studied in cycle 1, and will help us understand the formation of early evolution of planetary systems. It's a planet found in SCOSEN AB associations about 130 parsecs away. It's actually only 17 mega years old. It is extremely young, and it was found by Rizzuto as part of that time survey. And it's Andrew Mann's program that got accepted to do near-spec bright object time series observations. So they'll study one 5-hour transit in transmission and look for chemical patterns to reveal where the planet formed, typically by looking for carbon and oxygen ratios in the planet atmospheres. And as a result, can say, did it form far away from the star or nearby? But it's not TESS to not only help us look at young planets, but also mature planets. As in TESS discovered a giant planet transiting a white dwarf, possibly and as a result, it's giving us the opportunity to study cool middle-aged atmospheres, both in transmission and emission. There's actually 2 programs here, one by Ryan McDonald to study this planet in transmission, and one by Andrew Vandenberg, who was the discoverer of this planet, or the first author of the discoverer of this planet, I should say, to study it in emission. This giant planet is much larger than its white dwarf star, as you can imagine, which means that the features you get out of its spectrum, which is what I'm showing here, are going to be really deep. And so they'll be able to search for things like methane and ammonia, phosphine, and water in this giant planet. And so thanks to Ryan McDonald for letting me use this from his proposal for this talk today. And so the planet that was about halfway down was a Neptune. And this planet, LTT 9779b, is part of actually a guaranteed time observation where they're actually looking at the diversity of exoplanets using the nearest single object slitless spectroscopy phase mode, and looking at phase curves of exoplanets. What's unique about this planet, it is like the most highly irradiated Neptune-sized planet ever found, and you can see where it's located in either a mass or radius versus period diagram where there's no other planets. And it's because we believe that the atmospheres have been eroded away from these planets. So why is this one there? And hopefully Webb observations will give us some understanding as we constrain the temperature and pressure as a function of longitude for the atmospheres of this planet, and study how heat is distributed in its atmosphere. But as I promised, TESS's real significant contributions allow us to look at planets that are small. And this is where a lot of the hours are coming from, is there's a large program that was proposed by Batalla and Teskey. There's 146 hours, which you can't see on there, but it does say that they got for a large program. Large programs have no proprietary period, no exclusive access period, which means the data, when it's taken, will be free and available to everybody in the archive. And as a result, we're going to get a real sample of these sub-Neptunes and super-Earth planets with Webb. And they're going to be able to measure the relative abundances of molecular species and look for things like water, carbon dioxide, carbon monoxide, et cetera. And as a result, they're actually looking at multi-planet systems as well, some that are pairs, such as TOI 178b and D, where they can they'll be similar in one way. One is more highly irradiated or one isn't, or one's slightly bigger, one's slightly smaller, and they'll be able to look at things like, how are the atmospheres different between those that sit on either side of that gap that Benjamin Fulton found in 2017 when they looked at the Kepler populations. And also, as you get even smaller, we actually have a large population of Earth-sized terrestrial planets around M dwarfs. And there are several programs that are going to look at these. We're here, you know, these terrestrial planets, already M dwarfs, give us the best possible signal to look at atmospheres of a terrestrial planet because the star is so small. And so we're hoping that eventually we can use these planets to help us see if we can find terrestrial worlds with material that is maybe potentially contains things like we see here in the atmosphere of Earth, such as water or methane. But the first question is, do these planets have atmospheres at all, and which ones do? And so that's kind of the main question they're going after with these programs. There's a medium-sized program by Stevenson and Justus Jaeger with 76 hours to look at a collection of these planets. And hopefully they'll learn which ones actually have atmospheres, which ones have been eroded away by the high energy flares coming from the M dwarfs. And if they have them, we'll learn a little bit about atmospheric escape and constrain the impact of M dwarf irradiation on terrestrial planets. And then there's the super tiny hot ones. TESS discovered 2 planets that is going to give Webb the opportunity to study exoplanet surfaces by studying the thermal emission using the MIRI LRS program, LRS mode. It was LHS 3844b and GJ 367b. There are 2 programs to look at these, and if you remember Laura Kreiberg's paper from 2019 where they looked at Spitzer, she pointed out that from these from this phase curve that you could actually distinguish what the surface of the planet is actually made of, whether it's a granite or basalt. And with MIRI, you're going to actually complete out the data to match these kind of models. And also potentially look for volcanism on these planets. Is the planet outgassing, and look for evidence of sulfur dioxide potentially around these planets. So I have no doubt that this trend is going to continue. If you even look just at this meeting or very recently, there is already a new multi-planet, HD 260655, that was announced by Luque very recently. And it's orbiting a bright M dwarf, and it'll make a great JWST target. So TESS is obviously continuing to find new planets that are perfect for Webb to observe. And I look forward to seeing what it contributes to future cycles. And so I'll just leave you with this last thought that the TESS discoveries are really enabling the exploration of a diverse set of exoplanet atmospheres, especially giving us a nice population of those smaller than Neptune to study things like the forces that are shaping small planet evolution. And so I thank you for your attention, and I will happily answer any questions.
Thank you, Susan. If you want to ask a question, we have microphones in the front. You can also ask it on Slack or on the chat on WebEx. Nicole?
Okay, I'll ask one simple question. As the TESS discoveries are folded in to the process, how soon are you going to be able to get the ones that are in this first year of the extended mission program?
First year. So you're asking the planets that are discovered this coming year, and you can get them out how quickly? How soon can we? It looks like you don't have to confirm a planet to get it into the JWST observations. It's a bit iffy there on my research there, but
there's several steps, several courses, pipelines to identify.
Yep.
And follow up. In a number of instances, that's only been less than a month. That's what we should.
yeah, okay. So within 6 months, you potentially could have new targets, is what you're saying, from September. So those would make it into cycle 3 potentially, right? Cycle 2 is, I mean, if you come to the town hall, we'll talk about this a bit, but likely it's looking like cycle 2 proposals we do in January. So you'd make the next round, so it start to become a yearly cycle. That's okay. Honestly, you should need to go to JWST.STSci.edu, and that's where you can look up all these abstracts and what they're doing to get exoplanet observations, and hopefully you can use that as inspiration to put in more programs for the Webb Space Telescope.
Okay, any other questions? Okay, thank you, Susan. Okay, the next speaker. Next speaker is Michelle Kunimoto. Michelle is a postdoc at MIT, part of the MIT team working on TESS. Michelle is also one of the speakers, the experts, sorry, about occurrence rate of planets, especially with the TESS data, and she will tell us about what we can expect with habitable zone planets in the next extended missions, plural.
Great, thank you for having me here today. So I actually wanted to start off this talk with sharing one of my favorite images, which is the iconic pale blue dot taken by the Voyager 1 spacecraft. When I look at this image, I'm kind of, it really evokes a sense of why it's so important to look for other habitable planets out there in the galaxy. This isn't just a philosophically interesting question, and I think everybody has asked themselves at some point in their life, are we alone? But it's also a scientifically fascinating question, and one that exoplanet science is able to help answer. Now, in exoplanet science, when we talk about planet habitability, we typically talk in terms of the habitable zone, which is the range of distances from a star in which a rocky planet could have liquid water on its surface. Now, of course, not every planet in the habitable zone is going to be habitable or even have water, and not every planet that's outside of the habitable zone is necessarily not habitable. But this is basically just a first good guess where we can start to look for potentially habitable Earth-like planets. So what does this have to do with TESS? Well, just to give you a sneak peek to what I'll be showing in my talk today, as TESS continues to observe, its coverage of the habitable zone is going to continue to increase. And even with the prime mission alone, so the first 2 years of TESS data, we have coverage over a wide variety of the habitable zone. So specifically, there were 3 questions that I want to address today. The first one is, how many planets do we expect TESS should find in the habitable zone through the missions we've already had and the upcoming missions, particularly EM2, which will be the next 3 years of TESS data. And of these planets, what will be their typical planet properties, like their orbital periods and planet radii, and the typical stars that are going to be found around. And lastly, what kind of science are we going to be able to do with these planets once we detect them? Now, as Nicole mentioned, we've already successfully been approved for funding for another 3 years of the TESS mission for EM2. So looking forward to a potential EM3, I'm also going to be talking about how an extra 2 years of TESS data will impact habitable zone detectability. Now, one of the ways we can answer these questions is through simulations of the TESS yield. Now, because this is pretty key to understanding how I'm going to be coming to the results I'll share, just to give a very brief overview of how this works, what I'm basically doing is starting with a large number of stars that I expect TESS will observe over the course of its 9 years. In this case, I picked the 9.5 million stars in the CTL, of the candidate target list, which is a subset of the much larger TESS input catalog of likely dwarf stars that are particularly good targets for looking for planets that are detectable. Around each of these stars, I then simulate planets with various planet radii, orbital periods, impact parameters, all kinds of orbital and physical properties. and simulate tests trying to detect planets around these stars. Of course, not all these planets are going to be transiting, so they won't be detectable by TESS. And even those that transit may not necessarily have a strong enough transit signal in the TESS light curves to be detectable. But nevertheless, once we compile all the planets that are detectable by TESS, we basically have something that looks like this. So this is just essentially our simulated TESS planet catalog after what I expect the TESS will be able to find after EM2. Now, the full details of these simulations were just published in a paper within the last month, so I encourage you to look to those. But today I'll be just focusing on the habitable zone in particular. So for each of those detectable planets, I place them within or outside the habitable zones based off of the estimated insolation flux that they receive from their host stars and the effective temperature of their host stars. So after the 4 years of the TESS data, so essentially where we are right now, I actually predict that TESS should be able to find about 100 planets within the optimistic habitable zone, 10 of which are twice the size of Earth or smaller. And in terms of the conservative habitable zone, which is kind of a narrower definition, those numbers are roughly half. But the next extended mission is going to considerably increase the yields of habitable zone planets. In fact, I'm finding that the next 3 years of TESS data should roughly double the number of detectable planets that TESS can find in the habitable zones. And after a full 9 years of TESS data through EM3, that number should come up to about 272 total planets in the habitable zones that are detectable by TESS. And just to clarify, the planets that I've shown on the bottom that are marked as stars, those are all the planets that are less than twice the size of the Earth. So this is kind of a histogram of these planets that are detected as a result of their host stars. So what I've done is I've basically stacked the yields from each main mission on top of each other. So we can see that M dwarfs are going to be the most common habitable zone host stars from TESS, followed by K dwarfs and G dwarfs. But as we continue to observe with the TESS mission, we will be gradually increasing our detectability of planets in the habitable zones of F-type stars as well. In terms of the smallest planets, they were almost entirely going to be around M dwarfs, although in EM3, I'm estimating we may be able to find the first small habitable zone planet around a K dwarf star with the TESS mission. And this is a histogram of planet radius of all the planets that are found in the optimistic habitable zones. So really kind of the main takeaway here is that most of the habitable zone planets found by TESS are actually going to be smaller than the size of Neptune, or smaller than 4 Earth radius. The main reason for this is that they are intrinsically much more common than planets that are much larger, which makes up for their lower detectability. And this is a histogram of planet period. So you can kind of see that I'm expecting it to have 2 main modes, where on the left, it's centered at about 30 days, which is the typical M dwarf habitable zone orbital period. And on the right, it's centered at about 200 days, which is a typical K dwarf habitable zone period. So some of the science we can do with these TESS planets is really exciting because one of the strengths of TESS is its ability to identify planets that can be followed up with the radial velocity method. And this is really important because with TESS photometry, we have radius of the planets. With radial velocity data, we have the mass of these planets. And in the combination, we can estimate the density and thus the composition of these planets. So I estimated the RV stemming amplitudes that all of these detected planets would be able to induce on their host stars, and I'm plotting them here with host star V magnitude. Now, of course, because so many of these planets are found around M dwarfs, which are very faint stars, many of them are going to be likely too faint for RV follow-up. But if we were to focus on this kind of left corner here, where I'm marking all planets with a semi-amplitude of at least 1 meter per second, orbiting stars that are brighter than 13th magnitude, which is well within reality for even current RV instruments, you can see that TESS is going to be able to identify dozens of good follow-up targets in the habitable zones, including some that are smaller than twice the size of Earth. Another really interesting piece of science that I would love to be able to contribute to over the next few years is planet occurrence rates. So specifically, a well-characterized TESS planet catalog, where we understand the completeness of that planet catalog and the false positive rate, is going to have significant statistical power for improving habitable zone planet occurrence, especially for M dwarfs. So just to give you some numbers, the Kepler mission, which is where we have most of our occurrence rate understanding, observed about 4,000 M dwarf stars and found 22 planets in the habitable zones of those stars. By comparison, TESS is observing millions of these stars, and it's going to be finding over 100 planets. So this is a significantly larger data set where we can really improve understanding of the Earth-size, Earth-size habitable zone planet occurrence around M-dwarfs. Another thing to point out is you may have noticed that some of these habitable zone planets have orbital periods in the thousands of days. And this is beyond the sensitivity of the Kepler mission, which observed for only 4 years. So this is an area of parameter space that no other transit survey has been able to make planet abundance estimates for. So this is going to be something that's, that TESS is going to have a lot of potential to contribute to. So how do we optimize the TESS habitable zone yield? It's worth remembering that the simulations I presented make the assumption that we are searching every single star that TESS observes. And in reality, there is no planet search pipeline that is that complete. Most of them are only targeting a very small number of stars or maybe only bright stars. So how do we go about finding as many habitable zone planets as we can? So far, TESS has found 31 TOIs, if we ignore all the false positives that are in the habitable zone, which is about a third of the number that I would have expected given where we are in the TESS mission. So that means that there are dozens more habitable zone planets just waiting to be uncovered in TESS data, even with the data at hand. So if any of you are interested in designing your own planet searches, definitely know that you have the potential to find some really exciting systems. So if for those of you who are thinking of designing your own searches, just a couple of pieces of advice that I would give for optimizing the search for habitable zone planets. The first one would be definitely to focus on faint M and K dwarfs, which have been not observed by previous planet searches. And second of all, to keep in mind that TESS data does have these really large gaps in the data, which can challenge the search for long period signals. So this is kind of an open question that I think would be a really interesting line of inquiry. How do we optimize the search for long period signals in TESS data despite the fact that we have these large gaps? So I'll just leave my takeaway slides up and take questions.
Thank you. Splinter. Question we're talking about that PPC of private times around red dwarfs. You mentioned that's around 30 days. I'd like to something like how the 27-day sector durations have finding those planets.
Yeah, so with 27 days, we are going to only find maybe one transit of planets in kind of the typical M-dwarf habitable zone. But because TESS is continuing to observe not just more stars, but the same stars over and over again, especially in our camera 4s, where we have up to a whole year of consecutive data, this is really the kinds of stars that we're going to be able to increase our sensitivity to longer and longer orbital periods.
Other question? Hey, I was wondering if where most of the algorithm is. Second like there's like there's.
So I find that most of them are going to be coming from the full frame images. The reason for this is because the FFIs don't have any pre-selection of targets. So currently the 2-minute cadence targets are about 20,000 stars per month, but the majority of those are actually guest investigator targets, so not necessarily exoplanet hosts. So most of the planets that we're finding, especially as TESS continues, are going to be found around the FFIs.
Any other questions? Thank you.
This talk is recorded. We have all these predictions now recorded forever. We can test them sometime in the future. Okay, we are now changing gears. We are moving from looking for planets to looking for extragalactic transients, or specifically supernovae. And we will have Michael Fausnaugh tell us about some of the thinking of how TESS can work together with the Rubin Observatory to detect these objects. And if it sounds weird to you that TESS is detecting supernovae, well, you have not read Michael's paper from last year? Last year, yeah. And that's only the first in more to come. Okay, Michael. Yes, I can.
All right. So I'm Michael Fausnaugh. I'm a research scientist at MIT. My interests are in time domain astronomy generally, but extragalactic time domain astronomy specifically. So it is kind of a case of something completely different. And I'll be telling you about these synergies about TESS and Rubin Observatory. So these are two facilities that have as a core pillar of their science cases time domain investigations, so searching the variable sky. And to get us on the same page, here's just a quick gloss of some of the pieces of these different observatories. No advance. There we go. All right, so Rubin will do this 10-year legacy survey of space and time. Most of that time is going to go in the so-called wide, fast, deep survey. So it's a baseline of 10 years. And there's been simulations to look at what kind of data and cadence, especially, we'll get from Rubin. And those show that probably as a kind of baseline about 3-day cadence. So for one field in the sky, returning to it every 3 days. Rubin has 6 filters, U, G, R, I, Z, and Y prime. So the cadence in a single filter is actually longer than 3 days, about 15 days is the median value if you're just thinking about R-band images or I-band images. The main exception to the wide, fast, deep survey is the deep drilling fields, which are 1-day cadence, but again, they won't be visited every night in the same filter, so longer gaps between individual filters. TESS, on the other hand, is doing continuous monitoring, reading out the FFIs every 10 minutes, and that's going down to 200 seconds starting in October. So it's a really different time scale that TESS is sensitive to, minutes, hours, and days. And the baseline for TESS is also shorter, something like 27 days is a typical TESS sector, of course, some cases up to year-long light curves. But TESS has this very large field of view, and that's important because it means there's a lot of overlap with Rubin when TESS is observing the southern hemisphere. So TESS flips about every other year, and the next, starting in the south, will be January 2023. Is the next time TESS starts in the south. So at that time, Rubin will hopefully be starting its science verification validation exercises. And the survey is expected to start in no earlier than late 2023, maybe later. So this is science that's another 2 or 3 years down the line, but I think we can take some inspiration from the idea that TESS and Rubin very likely will be observing the same part of the sky just in about 6 months or 9 months or sometime next year. Now, the numbers I gave you for Rubin are not determined. The cadence has not been set. And the reason for that is that this cadence is actually pretty slow when it comes to time domain and various transient surveys. Like current existing transient surveys are observing the sky much faster than this. And this is enough of a problem for time domain cases that Rubin is still discussing what the survey might be, what the final cadence of the survey will be. We're expecting an announcement about that at the end of the year. But to give you a sense of why this is such a problem, here's examples of simulated light curves for what you might get. So this is a type 1a supernova in the different kinds of survey modes for Rubin, deep drilling fields in the wide, fast, deep survey. And you can see that these are very sparse light curves. There's only 3 or 4 points per object in the wide, fast, deep survey, which is kind of the majority of the data. So it turns out this isn't terrible for detection. Like the detection efficiency for transients is pretty high, but there's very little you can actually say about the supernova if you only have 3 or 4 data points. And that means that characterization is going to certainly be difficult if in something like this wide, fast, deep survey, but in many cases may be impossible. So the actual cadence for Rubin is likely to be faster. There's likely to be this rolling cadence paradigm where you visit a smaller part of the sky at faster sampling. So here's an example that's about once every night visiting the same field about once every night and getting 3 times the sampling as wide, fast, deep. And you could do a lot more with these supernova light curves on the right. But like I said, this question has not been settled what the Rubin cadence will be. And even if they do adopt a rolling cadence, it's possible it won't start until the 2nd or 3rd year of the survey. So in the interim, the time domain pillar of Rubin has this kind of sparser coverage, and that's principally where TESS steps in. Because TESS has this continuous coverage and it can get all of those shorter timescales from minutes up to days and weeks. So one way you can think of this is Rubin is the discovery engine, of course, and then TESS used to characterize the transients discovered by Rubin. So what I'm going to do in the talk is mainly tell you about what TESS contributes to the Rubin cases. At the end, I'll maybe spare one slide on what Rubin can bring to some TESS investigations. So we'll go through that. So the two main pieces are this visual classification idea where you have continuous coverage from TESS. You can just see what the transient was doing after it's discovered. We already do this for the existing ground-based surveys. So these are surveys like the Assassin survey, Atlas survey, ZTF. They'll report their transient discoveries to a central database, and we are scraping that database and looking for transients that are discovered while TESS was observing. So this is all of the transients that are in the TESS fields in sectors 1 through 51. They're color-coded by the survey that reported the transient. But the key thing to notice is that there's a huge number of them. It's over 5,000 transients. It's a really big data set of TESS light curves that you could potentially go in there and see what the objects were doing. And if you were to do that, you might find things like this. So there's lots of weird behavior in there. Here are just six examples of interesting things. 4 of them turn out to be cataclysmic variables and activity associated with accreting systems. You know that from the very sharp rise times and all the action during the decay and strange variations and oscillations and so forth. The one on the bottom right is bottom left, is a particular triumph for TESS. This is a stellar flare, which you can see if we zoom into the TESS light curve. It was discovered by accident by Gaia on this date with the vertical black dashed line. And the flare only lasts a couple hours, so it's only because TESS has a continuous coverage that we could know what this transient is. If you were to go try to follow this up, you just wouldn't see anything there. And so this is what it is for TESS. You have these continuous TESS light curves, so you can see what the transients are doing. I'll talk more in a couple of slides about what realistically TESS can do with transients found by Rubin. But I also want to explain the second main science case here, which is measuring rise times of transients, which is kind of a specifically important way to figure out what a transient you're looking at is, on the one hand, and on the other hand, is something TESS is uniquely suited for in a lot of ways. So here's 2 examples of supernovae. These are type 1a supernovae, so they're standard candles. I picked 2 that are at different distances so that they're at, they have different brightnesses and therefore signal to noise ratios. And the way the rise time works is you can see really clearly how there's a flat baseline, and after the supernova explodes, it brightens up and reaches some peak value. And you can fit a model very easily and identify the peak of the supernova and the time of first light, and that difference gives you the rise time. And the goal for something like this is to make this plot of rise time versus color, which is probably the most powerful way of discriminating between these different kinds of transients, figuring out what they are. And again, it's TESS that you would use to measure the rise time on these timescales of days to weeks, and Rubin that you would get the colors from. And my understanding of the proposed observing plans is that every field in a given night will have a measurement of at least 1 color pair in Rubin. Right. So so the hope is that you could use these 2 observatories to fill out this plot and gain a lot of diagnostic power in terms of what objects you're looking at, and also learn more about physics of these objects themselves, of course. So that brings us to the question of what overlap will there actually be? Because after all, Rubin is a 6.4 effective aperture telescope, and it's a fluctuated survey, so the vast majority of the transients are discovered at very faint magnitudes. And to give you a sense of that, I have this diagram, which is the Rubin filters, U, G, R, I, Z, and Y prime. On the left are the Rubin 5 sigma detections for a single visit. And on the right are where the Rubin detector saturates. And my understanding is you can't do reliable photometry on saturated targets in Rubin. So the left to right extent of this figure kind of balance the range of objects that Rubin observes. Now, TESS has a single filter, of course, and the effective wavelength is similar to I-band. So you can focus on that I-band row. And we found by binning the TESS light curves down to 8 hours, you can push as deep as 20th magnitude, which is really pretty good. Just to do apples to apples, the 5 sigma limit is more like 19.5, so that's what I've marked here. But even on 8-hour timescales, you can get down to 19.5 detections in TESS. And that means that the overlap region is that middle wedge there between 19.5 or 20th and about 16th magnitude where Rubin saturates. Of course, you can do photometry with TESS as bright as you would like, but for the purposes of this, we'll focus on stuff that's 16th magnitude and fainter. And a useful number to keep in mind there is that TESS can do about 1% photometry on 30-minute timescales at 16. And so that also means that there's a kind of different range of timescales you can probe in this figure. At the brighter end, at 16th and 17th magnitude, you're talking about minute timescales. And as you go fainter, you get up to hours and maybe some cases days. So the main thing is to convince you is that there's a big enough wedge here that there's going to be interesting overlap. And the question would be, what sorts of targets land in this region? So I'm going to give you a couple. I won't have time to go into much depth, but we could certainly talk about them later. The first are type 1a supernova. Standard candle is very important for cosmology. If you took a type 1 supernova and put it at 460 megaparsecs, it will have a magnitude around 18.5. So all of the type 1a supernova discovered by Rubin that peak at 18, or all the supernova within 500 megaparsecs or so discovered by Rubin are probably worth getting a TESS light curve if TESS observed it, because you can bin down to 8 hours or so and see what the supernova is up to in those times. TESS observed a tidal disruption event. So this is a case where a star falls into a supermassive black hole and is ripped apart. We were able to watch it with TESS rise from 20th magnitude up to 15.5 or so. The idea is that if you took this, and this object was discovered at 120 megaparsecs. So the idea is if you took this band and started shifting it to the left so that that upper limit, that peak magnitude, was around 18th or maybe 19th, you can see that the lower extent would be pretty far into the range of Rubin's detectability. So that means the volume that you can probe with Rubin is very large as you get very faint, of course, right? So the rates of these things are expected to be quite large in terms of TDEs that peak at 19th or 20th. And those would be the ones that you could get light curves from TESS. I'll also point out that if you go to the Million Quasar catalog and cut on objects brighter than 20th magnitude in the red band and that are in the south, there are 230,000 AGNs, and these are objects that you can have TESS variability on timescales of minutes at the bright side again and hours at the faint side. And you can have multi-band light curves from Rubin on timescales of weeks and months and eventually years. And this is maybe one of the most exciting science cases because variability at these different timescales is probing physical processes at different distances from the central supermassive black hole. So you can do everything from stuff at the inner edges of the accretion disk close to the black hole, out through the broadline regions, and eventually out to the surrounding dusty tori. And this is a huge sample with it will be unprecedented amount of detail on all these different timescales. And then the last thing is I'm showing two very high impact transients, the gravitational wave source GW170817 and a very fast luminous transient that's likely some strange stellar remnant, the 2018 cow. These objects were kind of anomalously close to Earth, and so were very bright. Again, if you imagine taking that peak magnitude and pushing it to the left, so you've got maybe 1.5 magnitudes up to something like 5 magnitudes to push these down, you're going to be probing a much larger volume of Rubin for objects that peak at fainter magnitudes. And that means that the rates of these things will be pretty high, and you can get these TESS light curves at 19th or 18th to get a better sense of what these things are doing. So all this is to say, given the large volume probed by Rubin and very high rates of transients, there should be a lot of objects you can observe with TESS. And this isn't just a matter of picking through archives and stitching light curves together and comparing things. The TESS data release is going to change. The part of the data release strategy will be modified in October, so that we'll be releasing data products every 7 days with roughly a day latency from download or faster. And that means that every week you can take transients that have been discovered by whatever survey, including Rubin, and see what they're doing in the TESS data. And this might be an interesting way to find young supernova, find objects close to the time of explosion, find very strange behavior on the rising part of the light curve. And all of that has implications for how you might coordinate follow-up. All right, so that is it for what TESS can bring to Rubin. I'll just have one slide on what Rubin gives to TESS. One thing is color information. So like I said, you should be able to get colors for every observation of Rubin. That's hugely important for extragalactic science with TESS, but I don't have time to talk about that. Another thing that's sort of interesting for TESS is the flux calibration across multiple sectors. There's a difficulty with TESS for the absolute flux calibration is more uncertain than the point-to-point precision. And so on the top, I have a quiet star, and on the bottom, a variable star. The top two panels are the raw photometry, so just putting down an aperture and seeing how the flux works. And below that are the systematic error-corrected light curves. And you can see that there's these big chunks and offsets, and in fact, for the variable star, the co-trending fails terribly. You could fix this if you had external data to calibrate to. A Rubin I-band light curve would be just about perfect because it will be sampled every 15 days. So that's about 1 or 2 points per sector. And it will last the whole year that TESS is observing. So you can actually know the flux calibration much more certainly. And that has some implications for science cases, such as measuring spin periods of red giants and doing astroseismology to look at how the envelope interacts with the core, and long-term AGN variability where it's stochastic in nature, and so you don't necessarily know if the systematic error is caused by the instrument or the AGN itself. Okay, so that is really the end of my talk. In some ways, it's very simple ideas. The real question is just how much overlap there is. So I'll leave you with this as just a reminder of how these things fit together, and hopefully we'll look forward to seeing this in 2 or 3 years' time. And with that, I think we can open it to questions. So thank you.
Thank you.
I was just wondering on that second last slide, that after the right?
So this is a bit beyond my field, so I don't have perfect knowledge of this, but it's a combination of understanding the spin periods of the red giants and getting the modes inside of the red giants. And the spin periods are long enough that you need the multi-sector light curves. Whether or not these are bright enough to do the astroseismology, I'm not sure, but I do know that there is some limitation in the flux calibration for TESS on that along those lines.
Okay, so you broke up this slide about so one of the things is from that do you think that the cortex, if they did not study the other things, so that they would just discover one and test background?
Probably not, because, well, so one thing is that the test data are free, right? And so you can always take the test data and see what it's doing, regardless of how Rubin decides to do its cadence. And I think it's a good idea for Rubin to be able to do some of its own characterization, both in terms of contingency planning, but also there is a lot of real estate down below the limiting magnitude of TESS, and it would make sense to have well-characterized light curves down at those fainter limits. So overall, I would say, I think the rolling cadence makes a lot of sense for time domain aspects with Rubin overall.
What's the advantage of Rubin?
Sorry, the difference between Rubin and ZTF along which? Yeah, very, very little in a certain sense, because these are all transient surveys. In some sense, they're trying to do the same thing. Rubin is should have a much higher rate of transients. And so in some sense, there's more objects to look at in TESS. I don't have the number for like the incompleteness of like where incompleteness starts in Assassin or ZTF, but Rubin will be more complete at these fainter magnitudes, and so you just get many more objects. Whereas there's not nearly as many because of the incompleteness in the.
The next speaker is Avishay Gal-Yam. Avishay he will talk about ULTRASAT and TESS. Avishay is the deputy PI of the ULTRASAT mission, which might be new to some of you here, so you're in the right place. Avishay is at the Weizmann Institute for Science in Israel, so if you thought your flight from the East Coast was long, his was much longer.
Thank you, Avi. So I'm glad to be here. I'm continuing on the path that the previous speaker set up to us to move away from the comfort zone of the audience, I'm sort of guessing. So I've been asked, and this is what I'll try to do, to describe some of the interesting science that could come from the synergy between TESS and ULTRASAT, which is a new mission that I will describe. And as you will see, the thing that those two missions have in common is that they have wide field of view and rapid cadence. So Michael described trying to push from several days to maybe 1 day, but as you know, TESS can give you a much shorter cadences, and this is also true for ULTRASAT. Okay, so what is ULTRASAT? It's a wide field near UV space telescope. It's quite sensitive. It's going to have about 300 survey power of Gal-X, which was the previously most powerful UV mission. And it will be launched to geostationary orbit 2025 for a 3+3 year mission. So 3-year main mission and 3-year extension by NASA. The mission will have two components, and most of the time will be spent on what we call the rapid cadence component, which will cover about 200 square degrees almost continuously every 300 seconds, observing the northern hemisphere for about half a year and the southern hemisphere for another half a year. And small discussions we already had with the test team seems that there will be a lot of overlap in where both missions will be pointing in terms of when and where they will be observing. The science mission is led by the Weizmann Institute, where I come from. The PI is Eli Waxman. And it's a joint mission of the Israeli Space Agency, our German DESI collaborators, and NASA is providing the launch, which also opens this mission for the US community. And if you want to hear more details or actually read more details, there are actually materials in the NASA booth in the display hall, so you can see there more details and take them home if you like, or talk to me later. Okay, so I think it's very exciting, this synergy between the two missions. I think what we saw from Michael's talk before is that it's actually hard to make TESS and Rubin work together because Rubin is slow and very sensitive, and TESS has a very fast cadence, but is more shallow. And I think in that sense, the synergy with ULTRASAT is much more obvious because in that sense, ULTRASAT is more similar to TESS. And I will spell out two science cases in more detail. But I think what we should all remember, even though I will tell you all kinds of stories, it's a new observational windows. If you say, what sort of timescales happen on 1 minute timescales? The answer is that we don't really know. It hasn't been charted seriously. There are some few examples. And so probably if we do a serious survey and spend a lot of time on that, we will find new things that some of them we expect and some of them probably we don't expect. Okay, so let's talk about exploding massive stars. We mentioned supernovae. So imagine a big star sitting somewhere in a distant galaxy or not so distant, and then it explodes. A lot of energy is released at the center of the star. Shockwave is propagating through the star. As soon as it breaks out, this shockwave from the surface of the star, this is when the first photons escape to infinity, and we as external observers will be able to eventually observe the explosion. We call this process the shock breakout flare. If you think about it, because of light travel times from the different parts of the star, if the star is spherical, you would get a temporal time scale for the shock breakout that scales like the radius of the star at the time of explosion divided by the speed of light, which means that if you have a well-sampled enough light curve, this will give you a direct measurement of the size of the star at the time it exploded, which is very, very difficult to recover once the star has exploded and everything is expanding at 10,000 kilometers per second. So this is really nice, a really nice simple measurement. All you need to do is to sample the light curve well enough, and the typical time scale for such big stars is about half an hour, which is definitely doable by those conditions, and you're done. However, just to complicate life, Goldberg et al. Published a few days ago a new analysis, a new theoretical analysis of the process, and I put in something that looks like a cartoon. On the other side, you will see this red simulation of an exploding star. But actually, what they point out is that especially red supergiants, which are the typical stars that explode as supernovae, are not really spherical in the sense that they have this convective structure and with different patches that have different conditions. So the shock doesn't break from the surface of the star at exactly the same time. And this difference is sufficient to smear the signal from maybe half an hour to a few hours. And in particular, the information, the direct measurement of the stellar radius goes away. In principle, this would have been a simple measurement that ULTRASAT could have been doing alone because you only need a measurement of the time scale. So now, at least if this analysis is correct, this can no longer be done. And here comes the impact of adding TESS. Because if you get ULTRASAT and TESS observing the same piece of sky, which will happen naturally, right? Because TESS is observing such a large sector that if the ULTRASAT field, which is smaller, is in that sector, you just get this from free. Nothing has to move. You get 2 points every sampling. You know, ULTRASAT is sampling at 300 seconds, TESS 200 seconds. So you will have simultaneous measurements in near UV and visible light, or near IR, and that gives you the temperature. The evolution of the temperature is a function of time, which we didn't have before. In addition to the time scale, which will probably be longer, you now have the temperature evolution. Now, it's still a matter for theoretical investigation whether you can recover the radius, but even if you cannot recover the radius with this additional information, it will definitely probe these inhomogeneities on the surface of the star, which if you think about it, is even more difficult to measure than the radius. The radius you can access in different ways by analysis of the emission later days. But this roughness of the surface of the star, this is really unique. And this, how much the temperature changes as in small or short timescale sampling is really unique. So I think this is really a fantastic thing. So this is really very nice. Now, what has been done so far? I have a missing slide here. Okay, let me look for it. Okay. What has been done so far? So people, of course, have been searching for this signal. And one of the famous attempts was done with Kepler. This is a figure from the paper by Garnovich et al., where the Kepler, of course, produced somewhat similar light curves to TESS in a slightly bluer band. And they were looking at a supernova and looking at the rise time of the supernova. This was previously shown. This is very interesting. And they saw this apparent small bump, which they interpreted as being the shock breakout flare. We reanalyzed the data and we found it's not significant. However, this demonstrates what you should be looking for, right? The supernova is going to become very bright in visible light. But before it gets there, there would be, or we are looking for this initial bump. It could be half an hour, it could be a few hours. This is what we'll be looking for. This event was at 400 megaparsec. It was too far, it was not significant. What it tells us is that we should move closer in. And when you try to find events that are closer, The answer is going wider, right? So you have more of them. This is, I shouldn't be saying this for TESS because it's obvious. So I did a rough calculation, estimation based on discoveries of supernovae from all the transient surveys that we have. How many of these we should have? It's closer than 100 megaparsec. And it seems quite likely that jointly ULTRASAT and TESS should catch at least one good nearby supernova like that every year. It's not going to happen every day, right? Because we are looking for the nearby events, and the nearby events are rare. But this has never been done. So even if we do one or two of those, it's going to be, I think, a very nice result and quite high impact. So that's one science case sort of worked in detail. A second one, which will reorder the slides, was also previously mentioned. These are rapidly evolving transients. So what you can see in this plot from Anna Ho, analyzing ZTF data, is that most supernovae have typical time scales of more than 10 days above half flux, right? If you measure by the time the event rises to above half flux, and then it stays there for a while and then falls down again, more than 10 days, these are common supernovae, thousands and thousands of them. If you look less than 10 days, there are actually very few. And if you look to the left side of that figure, you can see the different types of events. Some of them are just all kinds of fast supernovae, which are, to me, very interesting, but something more or less we know. But there are also these unexpected events like 18 Cow that was already mentioned, and others now that join this group, which seem to belong to a different group. It's not easy to interpret them as regular supernovae. And by the way, what to me is an alternative definition of this group, all of this group of the fast events cannot be explained as powered by radioactive decay, which is the powering mechanism for regular supernovae. So there's really a physical mechanism, a physical distinction for these fast events. What exactly they are? Probably more than one type of objects, very interesting. And here's another, when we guess at what we'll be seeing, this is from Armin Rest using Kepler data for one such event that happened to fall in the Kepler field. You can see the fantastic sampling of the light curve by Kepler. And TESS can do the same, and ULTRASAT also. Unlike this event where you have single band measurements, so you have this very nice structure there. Right? You see it's not, there's like a shoulder and all kinds of structure that we really don't understand what they mean. What we're missing is the color. The color gives you the temperature. We have observations of these objects, and typically, at least initially, they are well described by black bodies. So if you have luminosity and temperature, you have the radius. And this probes directly the physical mechanism that drives the explosion. For example, the two leading mechanisms for these types of objects, we said it's not radioactivity. One of them is that there's some strong interaction between an exploding object and some material around it. Different thing is that there is some engine inside, an accreting neutron star, an accreting black hole that pumps energy into the system. And those two things, if you have the evolution of the radius with time, could have very different behaviors. If there's a shock outgoing through some CSM, it's going out. The radius is not going to go down. Right? It's either expanding, or maybe if the shock is sort of stalling, it will be more or less constant. On the contrary, if you have some engine pushing in material into a nebula, and the nebula becomes more and more transparent as it expands, the area from which the photons escape could become smaller. So if we see something shrinking, it's not a shock. If we see everything that's always expanding, gives us an indication that this is the physical mechanism. So I think, and again, this is quite directly observable from putting together TESS and ULTRASAT. How many of those? Again, it's not a very common event, but it's also not very rare. And you see that Kepler managed to measure this it's much smaller field of view than both missions. So I think it's quite feasible that those will be found. There are additional science cases. I did not want to spend more time to keep on the schedule, but other types of supernovae have initially all kinds of bumps. Type 1a supernovae have bumps, which maybe tell us something about the progenitor systems. Superluminous supernova, we know they have bumps, but you've never measured them properly. and these missions can do it, and so on. One other topic I wanted to mention, discussed habitability, discussed stellar flares, right? We saw one example. I think really understanding stellar flares has, of course, an impact on habitability, because if you have a habitable planet that keeps being bombarded by very violent UV flares from the parent star, it's a problem. And to do that, you need to characterize the flares in terms of their spectrum, whether it's thermal or not. And again, measuring the temperature is important. And what is the correlation between optical flares and UV flares? Right? Optical flares we can measure from the ground for millions of stars. So measuring the fraction of stars that have optical flares is easy. But what you really care about is the UV flares, and finding this correlation is important. And as I said, this will open a new window of discovery, and this is a good time to stop for questions. Thank you very much. The UV photometric precision of ULTRASAT. Yeah, how does it compare to SWIFT favorably? We've done a lot of work recently on analysis of SWIFT UV photometry, and I think our conclusion is that it's not reliable to better than a few percent because of systematic effects that are difficult to take out, and I can expand on that offline. So ULTRASAT will probably do better. I think our goal is to go below 1%, and I think it's reasonable. Of course, we will never get to Kepler precision, and it's not what the mission is planning to do, but 1% should be fine. If you're thinking about planets, maybe we could do big planets like hot Jupiter, stuff like that. I don't think the precision will be sufficient for small planets. Yeah, but we'll have to see when the sensor is in space. Yeah.
Tomorrow and throughout Wednesday, if you want to talk more one-on-one about ULTRASAT, supernovae, stellar flares, and all of the above. Okay, we are moving on, and we need to do a switch. Okay, the next and the final presentation will be by Rebekah Hounsell. She'll talk about, as you can see, synergies between TESS and Rubin. I think Rebekah is one of the maybe very few people I know, or the only person I know that works on both missions.
Okay, thank you very much, and thank you very much for having me here. Thank you to the organizers, and thank you for the meeting organizers themselves. My name is Rebekah Hounsell. I am a support scientist in the TESS Guest Investigator Office at NASA Goddard. I also have another hat where I work on the Rubin mission as well. So I've been working on the supernova side of things for Rubin. So I'm going to be wearing both of my hats right now as I give this talk about TESS's precursor science for Rubin. Wonderful. Okay, so I'm not sure how familiar everybody in the audience is with Rubin. It is NASA's next flagship mission that is due to be launched in 2027. It is a wide field near infrared imager. Well, it has a wide field near infrared imager. It also has a prism and a grism and a coronagraph instrument, which we use for technology demonstration. It is a 2.4 meter telescope, so very similar to Hubble in that way. And its prime objectives are to understand dark energy, dark matter, and look for exoplanets. Here we have the solar array sun shield. It's a service spacecraft module, and it has this high gain antenna for quick transfer of data back to the Earth. So I really like this image here because when I say wide field, I really do mean wide field. So as you may know, this is the pillars of creation. And this beautiful image here is a Hubble image, as you see. And then as we scan out, we actually see the Eagle Nebula that the pillars of creation are in. And this is the wide field that I'm talking about that you'll get with Roman is 100 times the field of Hubble. And a very sensitive as well instrument. So I just want to talk a little about, we've had some great discussions here this evening, and several of the instruments that are on this timeline have been discussed. So James Webb, LIGO, we have Rubin, potential overlap with the second extension, which has now been formally approved, woohoo, with Pandora, and we talked about ULTRASAT as well. And, you know, as we look towards the future of TESS, you know, we hope that there'll be an extended mission 3, who knows? But even if there isn't, there's a lot of work that can be done in preparation for the Roman telescope, which is going to be launched in 2027. And there's a lot of overlapping science that we should really investigate. So just a little bit of a comparison here. When I talk about the Roman filters, we have 8 filters, a GRISM and a PRISM that I previously mentioned. And I'm also showing the TESS bandpass here as well. And you'll see that there is this overlap in the bandpasses. So we have the F062 in part, the F087, and the F106 in part as well. So there is some overlap here. Additionally, we're going to be talking about the sensitivity of the instrument. So obviously, Roman is a lot more sensitive, getting down to these magnitudes in an hour integration or 55-second integration for the 3 bands that I mentioned the previous overlap with. But TESS, depending on the background and crowding, it can get down to about 20th, 21st magnitude AB. Roman, however, will saturate around about 15th magnitude in some filters. So we're talking about this limited range overlap in magnitude space, but there is overlap. Okay, so I'm going to give again a bit of a brief overview about exactly what Roman is planning to do. So Roman currently has these 3 core surveys. We have the Galactic Bulge Time Domain Survey, which is the one I'm going to be focusing on a bit more tonight. The science of this is to detect exoplanets through both gravitational microlensing and the transit method. It will also enable studies of variable stars and provide insights into the structure of our Milky Way. It's going to be using the wide field instruments, so imaging of high stellar dense fields. Observing area, I believe, is 2 square degrees with a cadence of 15 minutes. And they're going to be these 6 72-day bulge fields as well. In addition, there is the High Latitude Wide Area Survey. This is to focus on measuring the shapes of hundreds of millions of galaxies and measure the distances of tens of millions. And then also we're going to be talking briefly about the High Latitude Time Domain Survey, which is to observe supernovae, type 1a supernovae, and other time domain focused astrophysical phenomena. Again, this will be using the wide field instrument for imaging and the PRISM for spectroscopy. And the cadence of this is about 5 days over a 6 months over a 2-year period, with a cadence of about 5 days, and potentially having both northern and southern hemisphere observing fields. This is a very brief and quick overview about the Roman core surveys, but you can find more about these online. So I love this. This is clearly showing the overlap and the differences between Kepler, TESS, and Roman. So we have the Kepler mission here. So this is, unfortunately, cannot see the bottom of my screen because I'm dictating, but it essentially, we are talking about the different fields. Ah, wonderful. Thank you very much. So yes, the Roman telescope is having this 1.6 degree cone that's going to be pushing out to about 25,000 light years. The Kepler Space Telescope and the Prime mission had this 12 degree cone, which was pushing out to 2,000 light years. And TESS itself is this 360 degree sphere, which is pushing out to 150 light years. So there is some overlap. And again, I'm showing the different methods that will be employed by Roman with regards to TESS. So it is using the transit method that TESS uses, but additionally, it's going to be using the microlensing method as shown down here. And we'll be using the technology demonstration, the coronagraph, in order to do direct imaging. Okay, so recently, as many of you obviously know, we have gone past the 5,000 plus planets confirmed. Over the past 30 years, we have done a lot of searches for exoplanets, and we've now hit this memorable marker. And when I wrote this talk, there were 213 planets confirmed with TESS, and another 5,000 724 test planet candidates. So this is amazing. However, in the future, Roman I'm just going to say, Roman is expecting to find 100,000 new exoplanets via the methods that we previously discussed. So the data hopefully will be amazing, and TESS has a lot to do to support this mission as well. So let's get to what I'm talking about here, exoplanet precursor science. So I do want to just say this statement of multiple techniques combined with data from multiple surveys are required to fully understand how planetary systems form. We need to find planets of all masses and at all distance to really understand what's going on. So the Roman telescope, so I have this plot here showing the Kepler. So we have Kepler, which has these, we have these larger planet masses with these smaller orbital distances, and Roman is really going to expand upon this. So Roman is really going to expand upon this. And when we use data combined from the TESS, Kepler, and Roman to fully understand how planetary systems form. So we need data from TESS and Kepler to inform the Roman mission and to fill in the gaps. So we need to create models, software, and to get expertise from the community to ensure accurate detection and classification of these planets and their hosts. And I do want to thank Matthew Penny. This has been adapted from their image. Okay, so as we know, the TESS mission is more than just an exoplanet mission. I believe that my co-speakers tonight have already touched upon many of these things. So TESS is a treasure trove for stellar astrophysics. So in this image here, TESS detects oscillations of 158,000 red giants. And this is work done by Honatar, in which they use the long period data from TESS and applied machine learning algorithms in order to detect these oscillations in these red giants. Now, red giant astroseismology is extremely important for understanding stellar populations and for understanding the Milky Way, essentially, in its evolution. By studying significant quantities and doing astrometric measurements, we can get a better understanding of the Milky Way and how it evolved. So, in Roman, through the galactic time domain survey, it should image and observe over 1 million oscillations of these bulge giants, essentially. So combining the data from TESS and combining that from Roman, we can get a complete picture of things. And additionally, we need to inform our decisions that we're going to make with Roman with our TESS data, which significantly widen the window and observations that we have today. Other word that I want to touch upon briefly, we talked, as some of my other speakers talked about flares and eclipsing binaries and cataclysmic variables, all things that TESS observed and improved observations of. So I just want to touch upon some of the work that was done by Dr. Ward Howard and by Adam Friedman. So Dr. Ward Howard and his colleagues used the UNC Chapel Hill Everscope telescope, and they simultaneously observed superflares. The team's work led to the creation of the largest sample of superflares observed at high cadence with multi-facility, multi-wavelength monitoring to date. Additionally, Adam Friedman used machine learning to sort through and classify over 70 million stars. He found systems in which there were multiple dimming events, which are thought to be due to the passage of multiple stars, so eclipsing binaries. Today, he's identified 8 eclipsing quadruple systems. So the techniques that are being built up in the community, these are going to be needed to apply and to inform software and tools that will be developed for the Roman mission. Okay, again, talking about more transient astronomy with TESS, so I really like this plot here. As we go into now the second extension of the mission, we have these 200-second full-framed images. This is really going to help us get a better understanding of some of these very rapid evolving transients that are occurring. So continuous coverage of the Morn TESS sector, so 27 days. We're really going to be able to get a better understanding of some of these rapid evolving events. And then having TESS multi-sector information is really going to help us understanding some of these things here, the Kolkat supernovae, tidal disruption events, flares, etc., etc. And considering the fact that TESS has observed almost the, well, has basically observed, will observe almost the entire northern and southern hemispheres twice by the end of the first extension, you know, we're building a baseline for understanding different types of variables and transient events. So I just want to show this nice little movie here that we have, which is really showing, again, we talked about supernovae. So these are some of the supernovae that have been observed using TESS. And hitting upon the fact that, again, we typically tend to miss the early rise and peaks of these supernovae. So by having the TESS data and coverage, we can really get this early rise information that can help us to distinguish between the different progenitor systems for type 1a supernovae. Getting this information will then also help us build models that we're going to need for the Roman mission. So I have been looking into the high latitude time domain survey, which is one focus of which is to look at type 1a supernovae and use them as cosmological probes. But getting models and information that we get from the early rise data from TESS, we can really help to inform these future surveys. And as I move on, oh, unfortunately this didn't play, but we'll move on from that. So one thing I really want to advertise right now is there was a recent ROSES call for the Nancy Grace Roman Space Telescope. And as I said, TESS data need to constrain the ages, rotation rates, and activity levels of nearby stars will be targeted in future direct imaging surveys for planets. It's also needed to create models of various kinds of stellar variation. So we need you to help and really inform the Roman mission. The ROSES call is out. You can go to the website that's listed here. There are the wide field science investigations. So I would strongly suggest you to look into both the PITS and the wide field science investigations and get involved with this mission. Okay, so my final slide here is the answer to the big questions that we need to understand is only going to be done through synergy with other missions. And I'm just finishing with this video here, and thank you very much for your time.
Thank you.
I believe a significant fraction of that is actually microlensing. And so when you're talking about the time frame for this, so the prime mission for Roman, I believe, is 5 years, with then the additional extension onwards. So I'm not exactly sure when these will be discovered. I'm assuming it's an ongoing situation. But obviously you'll have your planets confirmation, your candidates, and then your confirmations as we go through the mission. So thank you. No worries. If you want to learn more about the Roman mission, come to the Roman booth, and the same for science. Thank you.
So we do have some time. We have the room until 8 o'clock. So I want to open the floor to any questions to any of the speakers, or any questions about TESS in general, online or in the room. If not, we can stop here. I see there is still some food at the back of the room, so before it runs out, thank you everyone. Have a wonderful rest of the week, and see you next time.